So what I want to look at today is actually building on the stuff we've been doing with natural logs. Remember that our derivative of the natural log was 1 over x, and the derivative of ln of u is u prime over u. So thinking in terms of kind of the inverse nature of the integral and the derivative, it makes sense then that we've got this rule here for integration of the 1 over x. Now remember, on the power rule, we couldn't do the integral of 1 over x because we ended up adding 1 and then dividing by 0 because the exponent was the 0 power. Well, here, the integral of 1 over x is ln of absolute value of x. Okay? So notice here, there is a limitation. We have to include that absolute value there. But also notice, even with the u substitution, if we have the integral of the u prime over u, or the 1 over u du, it equals ln of absolute value of u plus c. Okay? So just to illustrate this a little bit, if I have the integral of 2 over x, you guys know we could rewrite that with the 2 outside. That's 2 times the integral of 1 over x dx. So that would be 2 ln of absolute value of x plus c. Now, just a side note here, what could we do with this one? We could actually do one more thing that would maybe make it simpler, depending on how you're thinking about it.
Split up the absolute value?
We could. I'm thinking kind of a different route there.
X squared.
What?
X squared.
Yeah, remember, if I have a coefficient here of 2, I could make that an exponent. And think about it. Once I make it x squared, I don't need the absolute value anymore, do I? Because if I square something, it's going to be positive. So ln of x squared plus c would be another way that I could write that same answer. Okay? Let's try this one. Here we're going to need to use a little bit of u substitution. Okay? So what is u going to equal here? Yeah, 4x minus 1. So the du is 4dx. Okay? So I need to incorporate the 4 here, which means I need a 1/4 out there, right? So I have 1/4 times the integral of 1 over u du, and now I can go ahead and take the integral. Okay, so it's going to be 1/4 times ln of absolute value of u. Since there aren't bounds that I can convert to, I should go ahead and give my final answer in terms of x. So that means I'm going to have 1/4 ln of the absolute value of 4x minus 1, and then a plus c at the end.
You bring it back up, or
You could, a 4th root. Although that still incorporates a plus or minus aspect, so it wouldn't get rid of the absolute value in this case. All right, here's another one. How would we approach this one?
u 3 minus x cubed.
Yeah, let's make the u a 3 minus x cubed. What's our du?
Negative 3x squared dx.
Negative 3x squared dx. So I need a negative 3 there. So I'm going to have a negative 1/3 outside. And here we go. We've got a negative 1/3 integral of 1 over u du.
So negative 1/3 times square root 3 minus x.
Negative 1/3 times ln of absolute value of u. So negative 1/3 ln of absolute value of 3 minus x cubed plus c. Okay? So again, with each of these, it's same kind of integration techniques. We're still using u substitution and whatnot, but it's just a new rule now. Okay? Now, here is a challenge. It says use logs to find the area bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. Okay, so what we're trying to do here is find the area under this curve. Okay? Now, between 0, well, does it hit 0?
Yeah.
0, 0?
Mhm.
Yeah, okay. It looks like it, but we should double check. If you plug in 0 for y, then x would equal 0 as well. So that is the point 0, 0. So really what we're trying to do, we're going to use logs to find the area, so the integral from 0 to 3 of x over x squared plus 1 dx. Okay?
You just make it x squared.
Yeah, so let's go ahead. We'll make the u the x squared plus 1. Now if we do that, the du is 2x dx, which again incorporates, we need to put the 2 here and a 1/2 out here. Okay, so that leaves us with 1/2 times the integral of 1 over u du. Now, since this is a definite integral, we do need to convert those bounds. Alright, so 0 as an x equals what as a u?
What?
1. 0 squared plus 1 is 1. So now our bounds are going to go from 1 to 10. Okay, 3 squared plus 1 will be 10. Okay, so we now have 1/2 ln of absolute value of u evaluated from 1 to 10.
Could
Okay.
you have, instead, if you didn't want to change the bounds, could you just substitute x squared plus 1 into the u?
Yeah, you can. You can always do that. Alright, so we use our fundamental theorem of calculus. I'm subtracting logs there, so I could go ahead and divide, or I could just recognize that ln of 1 equals, what's ln of 1? 0. Okay, so this just equals 1/2 ln of 10. Okay, or if you want ln of radical 10, but it's not any real simpler.
And then would you want us to, like, get the decimal and all that, or it doesn't really matter?
You don't have to, no. Alright, so that brings us to some other rational functions here you see in example 5. Now, not all these are technically rational functions. Here you have a trig ratio. But I want you to think through a little thought process, or I want to give you a little thought process for when you have rational functions. Okay, because all of these are cases where, you know, we're doing the integral of 1 over x, or we're doing the integral of some kind of fraction like that. So when you see a fraction in your integral, there's a couple of things that you can do. First of all, make your life simpler. If there's only one term in the denominator, you can rewrite that as separate fractions and reduce each one. That's particularly when you're dealing with polynomial expressions on the top, and you have just you know, something x on the bottom. You separate that up, and then you can do each integral separately, rather than trying to do, you know, whatever else. Okay. The second part is think about, is this u prime over u? And if it's not exactly, can you do u substitution? Alright, so like the second and third, that's what we're doing in this lesson. If you cannot, and this is what we'll do a little bit tomorrow, or later, if you can't do u substitution right away, and you can't just multiply by a constant to do u substitution, then what we're going to be doing is doing some polynomial long division. Okay? And you'll see how that works when we get there, okay? But we're not quite there yet. Let's take a couple minutes, though, and I want you guys to try these 4, and then we'll look at them, the full solutions. But I want you to try to work through this on your own first. Alright, so while I've got the screen frozen here, what did you guys get for A?
ln
ln
of the
absolute value of x
cubed
cubed plus x plus c.
Okay, ln of absolute value of x cubed plus x plus the c. Okay? Good. How about B? The trig ones can be tricky.
Absolute value of tan x plus c.
Okay, the u was tangent. Alright, so ln of absolute value of tangent plus c. Those were nice because the du was already in there. You just had to see it. Okay? These last two, we got a little bit of working to do. Alright? The c was missing a factor of 2, so we had to multiply by the 2 and then multiply by a half on the outside. Okay? So, let me unfreeze here. Okay? So, there you needed the 2. And notice here, it may be a little bit whatever to see it as 2x plus 2, and you've just got an x plus 1. But if you factor out that 2, it's easier to see. I'm missing a factor of 2. I need a half on the outside. And we have 1/2 ln of absolute value of x squared plus 2x plus c. And then D, we're missing the 3 in the du. So we multiply by a 3, multiply by a 1/3, and we get 1/3 ln of absolute value of 3x plus 2 plus c. Okay? Now, one note here, if you notice, none of these functions were this way, but if you notice that the u that you have is always going to be positive anyways, then the absolute value is not necessary. Okay, so if you had some kind of a function like e to the x or something that's always going to be greater than 0, you don't need to throw in the absolute value because that's just redundant at that point. But then you're doing ln of e to a power, so you could simplify that a little bit too. So anyways, so that's our introduction here to doing integrals with the logs. Okay.